Hello, I'm Professor Von Schmohawk, and welcome to YU. In the previous lecture, we saw how to construct a two-dimensional Cartesian coordinate system, which allows us to graphically display ordered pairs of real numbers, or sets of these ordered pairs, as points in a plane. We did this by taking the Cartesian product of the one-dimensional number line with itself to form the two-dimensional Cartesian plane. In this lecture, we will construct a three-dimensional Cartesian coordinate system, which will allow us to display ordered triples of real numbers as points in three-dimensional space. The set of real numbers R can be thought of as corresponding to a continuum of points in one-dimensional space. It is this space which is represented by the number line. Each real number corresponds to a unique point in this one-dimensional space. We then created a two-dimensional Cartesian coordinate system by taking the Cartesian product of the set of real numbers with itself to form an infinite set of ordered pairs called R squared, or more commonly R2. R2 corresponds to a continuum of points in the two-dimensional space represented by the Cartesian plane, and each ordered pair of real numbers corresponds to a unique point in this two-dimensional space. However, we are not limited to forming Cartesian products of only two sets of real numbers. We can also form the Cartesian product of three sets to form the set R3. Just as the set R2 consists of ordered pairs whose elements can be any two real numbers, the set R3 consists of ordered triples whose elements can be any three real numbers. And just as the two-dimensional Cartesian plane was built from two number lines oriented perpendicular to each other, three-dimensional Cartesian space can be created by taking three number lines and orienting all three perpendicular to each other. These three axes are typically labeled X, Y, and Z, with the positive x-axis pointing out of the page, the positive y-axis pointing to the right, and the positive z-axis pointing up. Just as in two dimensions, the point where the three axes meet is called the origin. The origin corresponds to the ordered triple 0, 0, 0. The three axes can be oriented in any way, as long as all three axes are perpendicular to each other, and they conform to what is called the right-hand rule. The right-hand rule states that if you align the thumb of your right hand pointing in the positive direction of the x-axis, and your index finger pointing in the positive direction of the y-axis, then your middle finger should point in the positive direction of the z-axis. For example, we could arrange the axes so that the positive x-axis points to the right and positive y points up. In that case, the right-hand rule tells us that positive z must point out of the page. Or we could orient the axes with positive x pointing up, positive y pointing out of the page, and positive z pointing to the right. However, the typical orientation is with positive x pointing out, positive y pointing to the right, and positive z pointing up. In three dimensions, just as in two dimensions, the infinite plane containing the x and y axes is called the xy plane. Likewise, the y and z axes create the yz plane, and the x and z axes create the xz plane. These three planes divide the Cartesian space into 8 regions called octants. The octants are numbered 1 through 8 and are typically labeled using Roman numerals. Just as the two-dimensional Cartesian coordinate system allows us to graphically display ordered pairs of real numbers as points on the Cartesian plane, three-dimensional Cartesian coordinates allow us to display ordered triples as points in Cartesian space. The elements of an ordered triple corresponding to a point are the coordinates of that point. To locate a point in this three-dimensional space, starting from the origin, we move along the x-axis a distance and direction specified by the x-coordinate. Then from that point, we move parallel to the y-axis a distance and direction specified by the y-coordinate. And finally, we move parallel to the z-axis a distance and direction specified by the z-coordinate. This determines the position of our point in Cartesian space. Another way to look at this is that the x and y coordinates locate a position on the xy plane just as in two dimensions, and the z coordinate specifies the point's distance above or below that position on the plane. Now that we have a way to visualize ordered pairs of real numbers as points on a plane, or ordered triples as points in space, the next step will be to create sets of ordered pairs which represent relations between different types of quantities. If the quantities can be represented by real numbers, then these relationships can be visualized in two- or three-dimensional space. We will do this in the next lecture by introducing the concept of a binary relation.